There we go.
And Chris Anderson, if your dog is going to continue to bark, can you please mute yourself? Was that an answer?
I muted him.
Thank you.
Oh, all this comic relief.
Should make it easier.
Yeah.
to slide into
So
things.
I'm gonna try to provide information on why you might want to learn to model and some of the very basics of modeling, and demo a inverted V NVIS 40-meter antenna. Without getting into too much detail, there are kind of two predominant antenna modeling programs that are used in the amateur radio community. And one is SLAARC 2. It's free, but it has some limitations. And there's EZNEC, also from W7EL. It ranges from $100 to $700. There's a demo program that you can get to get your feet wet. And there's a companion program. I won't go into that. I have EZNEC 6 Plus that was around 150 bucks because the first project I did was for WA8RA Bruce, and it was a 160-meter 4-square vertical array with an elevated ground plane. So it took quite a bit of power to do it. I'm also working on a hex beam that we talked about in December and a high gain Yagi for TV. I can't really advise anyone on the alternative modeling software, but I understand Steve has some experience with SLAARC 2. But I'm guessing that the fundamentals are pretty much the same, and it's just the interface and the limitations of the program that make up most of the differences. One thing about modeling is that most antennas are already modeled. And so essentially, you know, it may be in a different band or optimized for a different part of the band than you want. But if you take a model that's already been created, it saves a lot of time. And they're packaged with the modeling software when you buy that. They also come from the ARRL antenna book. There's a CD that's attached, and it has a number of models. So one of the things about EZNEC, I don't know if this is true for SLAARC 2, you always start from a designated model. There's no such thing as a clean sheet of paper. If you truly want a clean sheet of paper, you take a model and you erase everything and start from there. There's no way to open a blank sheet of paper. So what I'm going to do is give a demo, and any questions, kind of bring them up as we go, because it's difficult to flip. I'll be flipping from model to model, from input and output for those. And it'd be far easier if you ask your questions when we're on the right picture. The pages that I sent out were kind of the dimensions of that we would put in the models. I've already got the models created, but I handed those out so you could see how that related to the piece of wire hanging in the air. And if you want additional readings, there are a lot out there. I can provide a list. I've already given you a series of 4 articles by L.B. Siebeck that were published in QST, and they are great articles to get started. CBIC also has a website that has a lot of information on it and modeling. So with that, I'm going to try to share a screen and pop up the first. Oh, before we get started, one other thing. We're going to be talking about a number of different models that have different variables in them. So what I was hoping is that I could get 4 volunteers to keep track of, as we go through a model, a specific parameter. So after we've been through several models, you can relay how those changed, at the outputs changed as we changed the inputs. Okay. So one of the parameters is the resonant frequency. I believe Mike already volunteered for that on Saturday. Are you still good for that?
Yep.
Okay, who wants to be the person that tracks the SWR at resonance?
Oh, can I please?
Okay, Cease, it's you. How about the impedance at resonance? Come on, Jerry.
Sure.
Sure? Okay. And the gain at a specified angle at resonance.
Yeah, I'll do that.
Okay. All right. And lastly, I want some feedback after we're done with this, because there's I'm doing another presentation for a club down south, Doug KM4LKC, who's with us today, is a member of that club. And I'm hoping to get feedback also from him on you know, the differences in the club and how we might want to modify it. The variables we're going to be looking at are the angle of the inverted V, the height above the ground of the antenna, the wire length, so we can tune it, and various ground types. So with that, let me pull up let's see here.
Now, those of us that are keeping track of parameters, are we going to have just antenna 1, antenna 2, antenna 3, antenna 4 for the parameter that I'm keeping? Is that how we're going to do it?
Well, they're all going to be the same antenna with one parameter change. So let's say we change the angle of the V. How does that affect the resonant frequency?
Okay.
So that's
variation A through Z then.
Yeah,
Of
exactly.
a single antenna. Okay.
Yeah.
Just trying to figure out how to write this stuff down.
Yep. Okay. You'll remember I said you always start from a model. Okay. And this right here is the model, which is a backyard inverted V. Can you see me now, or I'm not on share yet?
You're not sharing it yet. We see you.
Yes.
Yeah, we probably ought to do that. What the heck? And it is right.
And Jerry, can you spotlight Bob so that?
I just did.
Okay, fantastic. Thanks.
Okay. So this is the interface of EZNEC 6. And I've loaded a model, which is kind of a generic backyard inverted V. And I'm going to open it and grab this to make sure I've got the right one. Just a quick view of the antenna. What you're seeing is the inverted V here. And right now, the V is on the ground, okay? Just like in real life, it's easier to do the model on the ground and then move it up off the ground. And so the way we do that is, here is the wires. Well, let's see, I'm going a little too fast. Let me back up for a second. Right here are the inputs, if everyone can see that. And
Yep.
right here tend to be the outputs, okay? So you put in a frequency that you're going to be at, it calculates the wavelength, and that wavelength is used by the program to make sure that the segment lengths that you're using are appropriate for the model. There is a wire section in which you describe the wires using Cartesian coordinates, X, Y, Z. We'll go into that in a minute. You use a source to drive the antenna, and I'll get into why later. You can add loads to the antenna, transmission lines, although they're ideal transmission lines, transformers, L networks. You can change the type of ground. You can change a description of the ground, which impacts the radiation pattern of the antenna. You can add loss for wiring, change the units. I'll be using 3D plots, and from the 3D plots, pull off 2D plots so that you can see sections through it. And then these are some of the issues you can use for changing references and the step size in the wireframe of the radiation pattern. The outputs, one of the critical outputs, it's not really an output, it's input, is antenna notes. And I don't have one for this because it's the generic model, but the antenna notes are a really good place to put tracks down of what you're going to be doing with this specific model. So a week from now, when you end up with 26 models, they're all on with variations on a theme, you can recall what it is that that model represents. This is, you can show the profile of the currents, both in text and pictorially, source data, a description of the source, load data, description, far field radiation patterns, near field radiation patterns, standing wave ratio, plot versus frequency. You can actually pull up a view of the antenna like I did earlier. And then this is the main radiation plot, a far field plot. Okay, so, and there are various options you can do. And quite frankly, I'm not going to spend the time. I'm just trying to keep this relatively simple. So let's start with wires. Can you see the wires frame? The wires?
Not now.
No. Oh, so that means I gotta reshare it.
Yeah, you can share your whole desktop or a specific window.
Okay, how do I share the desktop?
You have to close what you're presently sharing.
Okay.
Well, I mean, go to the top of your, yeah.
Yeah.
So then go to share screen.
Yeah.
And it'll show you images of all of the things that you can share. And one of them should look like your whole desktop. You'll see all of the individual windows, and one should be your whole desktop.
Oh, there it is. Okay. Now, are you seeing anything at all?
Nice.
Your desktop.
Okay.
Yep, we got the whole thing there.
Again. These are warnings. Okay, now these are the wires. Can you see them?
Yeah.
Okay. So what you have to do is describe the wire in Cartesian coordinates and insert them there. So what you'll see is we have a wire, and let's look at the antenna so you can visualize it first. The wire goes up and down the y-axis, and it's centered on the x-axis so that this number is the positive and this is negative of the same number, okay? And x is always equal to 0. The radiation field obviously is down x, and z is the height. So,
Bob, question.
yes.
How close do the endpoints have to be for it to consider it a connected wire? You're carrying 4 decimal points there. Does it just have to match on this screen? Is there a tolerance on that, or?
There isn't.
So as long as those numbers match, it'll assume that it's a connected wire?
Correct.
Okay.
Okay. And you can see the description. This is the second wire, the first wire. And over here, you specify, here's the diameter of the wire. The number of segments on the wire is a very important thing that we'll get into. And then if it's an insulated wire, this is the dielectric constant and the thickness of the insulation. 1 and 0 represent a bare wire. So right now I'm showing a bare wire. Sources, you'll see on this diagram, well, first of all, does everyone know what a current source is?
Well,
Sort of.
Sort of. Well, a current source is a source that puts out current that you specify, and it has infinite impedance. A voltage source is a source that puts out voltage, and it has 0 impedance. Okay? Now, for this program, there's also 2 other kind of sources. There's a split current source and a split voltage source. Okay. If we look at the picture of the antenna again, what you see is 2 circles up here. And those are a split current source. And the reason why you want to use a current source at the antenna is so that the source doesn't impact the what the antenna is. In other words, the impedance at that point doesn't change because of the source, because the source is infinite in impedance. So there's 2 ways to do this. You can use one split source, and you only actually input 1 in wire 1, and it looks for a symmetrically opposite wire, and it will stick in the other half of the split source. Okay?
Does that model where the wire is being fed with current?
Yes, that's exactly correct. Now, one of the things that's kind of weird about modeling is everything happens at the center of a segment. If you connect a transmission line, it has to be connected to the center of a segment. And a segment is a parsed piece of a wire. So right now, these, if I zoom in, and I'm going to have to lower it so that we can see it, and I'm going to have to try again. Okay, there it is. That's the bottom. So let's take this and bring it down right there and then zoom in a bit and make this full screen. And if you look very carefully, you see this little green dot there?
Yep.
That is the end of the segment. Okay. And if I raise this, you can see the end of the next segment right there. I've specified 5 segments for this wire. Okay. What that means is when the model calculates things, it assumes everything on this entire segment is the same. So the current over this entire thing is an average of the center of that. So you can imagine the coarser this is, the fewer segments you use in describing a wire, the less accurate the model will be. Everyone got that?
Yep.
So,
So to clarify, what you're saying is if you've got a wire that is 30 feet long, you can have 2 segments of 15 feet apiece, or you can have 10 segments of 2.5 feet apiece. And the,
exactly.
and the segments are just an artificial way of looking at a piece of the wire.
Yes, but they're also the critical element in which the calculations occur by the NEC engine around the characteristics of the antenna. So if you only have 5 segments, it's only looking for 5 currents on that piece of wire, okay? And it uses that to calculate the fields. So if you have 50 segments instead of 5 segments, you have many more descriptions of the current along that wire, and you get a much more accurate model or representation of the impedance, the SWR, the radiation pattern, okay?
It's like fine tuning.
Exactly. Now, you can actually make too many segments because there is a minimum wavelength percentage that you need to have in a segment, okay? I won't get into that today, but trust me, if we were to use 500 segments to describe that wire, okay, the program would go tilt. Your segment lengths are too short.
Well, the other problem, Bob, is CPU horsepower.
That's correct.
I mean, there's a trade-off here between CPU horsepower and how long it takes to do these calculations and to do the 3D model. If you have too many segments, you can go get lunch and come back before it's done modeling.
Yeah, well, that's more of a problem with NEC 4 than it is with NEC 2, but yes, that's true. With modern computers like this one right here, it will crunch through. I've had like 1,800 segment antennas, and it'll do them in a minute or two. So it back in the old days, that was really a problem.
Right now, isn't EZNEC limited by the number of segments you have? You can, that's what you pay for. There's a free version that'll give you 10 segments, and
yes,
and the advantage of 4NEC 2 is there's no limit on segments.
Well, the 4NEC 2 is a totally different number crunching engine. Okay.
Yeah.
All NEC 2 programs use the same number cruncher, although they may be limited in the number of segments they'll digest. And that's an artificial limitation so that you can pay more for more segments, okay? I have 2,000 segments, that cost me $150. If I wanted 5,000 segments, it probably would have cost me $300 or something, okay? So I figured 2,000 was enough, and I hoped it was enough, and it's turned out it's enough, okay? This right here, this blue on the wire, says this is the one on a split source that I've put in. This is the one that will show up in the source list, but it knows to put one here in the symmetrically opposite segment. So that's the split current source. Now, what if you didn't want to use a split current source? You could put a third wire that went from here to here. I'm sorry, I'm using my pencil. From here to here, and then put the source in the middle, put a current source in the middle of that. That's another way to do the same thing. Obviously, that is more prone to error unless you're using a lot of segments. Understood so far?
Okay.
Okay.
Good enough to presume that leads us somewhere else.
Okay. What we're going to do now is actually load a model. And this will be the first one that's in the batch that shows antenna parameters of a total height of 23 feet, 117-degree angle, a 32.5 foot wire, okay? Okay, now, if you look at this, you can see the height is 17 feet, and we see 23 here. That's because this thing is 6 feet off the ground. So the way you would really construct this, particularly if it was a difficult one, is, okay. And now you can see the 17, which is on the page here as big H, and you can see the 27.7, which is the big D, and it's on the plus Y and the minus Y axis.
Bob, while you've got that screen up, let me ask you a question about the wire diameter. Does that pound 12 mean 12 gauge, or I'm sure
It
it's not
does.
12? Oh, okay, well, they said, but they say in inches, so obviously it's
Yes.
gauge, not inches.
If you
Okay.
put a pound in front of it, it knows it's gauge.
Okay, good, thank you.
Okay, or you can put in the dimension of it. I have increased to 10 segments because I did the study that said, here are the answers at 5 segments. Here are the answers at 10 segments. They're enough different that I want to move up to 10. I also did the study that said, here are the answers at 10. Here are the answers at 20 segments. And the answer wasn't different enough to worry about it. So that's kind of how you figure out how many segments you're going to use in your model. You'll also see here that this wire, which is specified as, it's a flex weave. It says 14 gauge. I thought it was 12 gauge, but I did the whole thing in 12 gauge, so we should be okay. With polyethylene insulation, and the polyethylene insulation from their spec sheet is 0.023 of an inch thick. So if you look here, anyway, I don't know why it's not doing it, but it may be because it's already in there. Normally you can pull it up and it will have the various materials with the various dielectrics for them. Plus you can set up custom wires, like I have one in there for flex weave. So whenever I get a flex weave wire, it puts 2.26 in with 0.023 thickness. Okay, that happens automatically. So now if we were to say, okay, we're done, I've made a mistake on purpose, and we go back to this, there's something called a geometry and segment check. And it runs through and it says, this might be an error you need to look at, okay? And you ought to go back. And here's my warning. Warning, the wire connected to a real non-mini neck ground. See manual, okay? Turns out with a real ground, you can't connect a wire to ground. You have to use a mini neck ground in order to connect a wire to ground. That's one of the limitations of the NEC2 engine. An NEC4 engine has more capability in modeling grounds, okay? So the reason why we're seeing this is because I forgot to raise the antenna back up in the air. It's sitting on the ground. So we'll change the height by 6 feet, move it back up, everything's copacetic. When I run the outputs, the geometry check, you see the warning's gone. Okay, so now let's do something with this model. What I'm going to do now is run the SWR plot, and you can specify from where to where and how fine a step to make. Okay, so, oops. Here's the plot of the SWR versus frequency. And we were desiring to have it at 7.150. And if we look down here in the lower left-hand corner right here, we can see what the impedance is. And since we have a positive impedance, there, it goes from positive to negative right there, okay? And this is 0.01, and that's 0.2, so 0.01 is closer to 0, okay? And the resonant frequency for this model at an angle of 117 degrees is 7.175 megahertz. The SWR of the antenna at resonance, this may not be the minimum SWR, but it is the SWR at resonance, is 1.098. The impedance at resonance is 54.89 ohms.
Are these the numbers you'd like people to write down?
Yes.
Already done.
Okay. So, and of course, you can look at this at, let's say you wanted to look at it at 75 ohms. There's a 75 ohm sweep in addition to the 50 ohm inherent impedance sweep. Okay. Now, let's take a look at the field. There it is. Okay. If we want to take an azimuth swipe through that.
Can we see the antenna in there? I'm not.
The antenna, you'll remember, goes up and down the y-axis. Here is
Okay.
the y-axis. Do you see it?
Yeah.
Okay. So now I've put a slice through there. You can hardly see it, but it's there. And there it is, okay? And what it's showing you is that the gain, the max gain in the 3D mode is 3.11 dBi, and the angle that that max gain occurs is straight up. If we look at the elevation plot, it's a little easier to see that, okay? So this antenna at this height is radiating a lot of energy straight up into the clouds.
What are the
Thus the
purple ones?
expression, a cloud burner.
That's exactly what it is. And, but it's an NVIS, which is an antenna that's meant to be for a small local area. It's not for DX. And I think these are the 3 dB points right here, the purple lines.
Ah.
Okay. So you have a beam width there of straight up. And if you want to look at different elevation slices, obviously you can,
And this is looking broadside at the antenna, I assume. So it would be in the plane of the screen.
correct. And
This, I have
as you
this
walk,
very
go
antenna.
around in a circle, okay, around the antenna, you can see it change, okay? Or if we look at an azimuth plot, okay, and walk down the antenna, you can see how the radiation pattern changes depending at what elevation you're at.
Huh.
So, you know, about 30 degrees, you've got kind of the normal dipole pattern that you'd expect. But as you go down, it turns into a circle. And it's also a circle up at the top. And that's because the V antenna, the vertical aspect of it predominates versus the horizontal aspect of it when it's like this. Okay. So next thing, everyone got that so far?
Yep.
Clear as
Okay.
mud.
Clear as mud. Yeah. Well, there's a lot here to take in a short period of time, and I'm sorry about that.
No, that's all right. I'm getting it.
Okay. Oh, I forgot to do that. And here are my notes, which I keep track of what is this model parameters. And so I've described it. Its apex is at 24.6 feet. The V angle is 117 degrees. Here's the resonant frequency and so on. Okay. And that's the antenna notes piece. So let's open the next model. I changed something. I wonder what I changed. Oh, one of the things I didn't talk about is the ground here. Let me do that real fast. Different ground types can be used. There's a free space ground, which means the antenna is somewhere between Mars and Earth, and you get very different kinds of radiation patterns because there's no ground to interact with the antenna. So if we were to look at that plot, you can see it's a sphere. Okay, because there's no ground underneath it. Or you can have a perfect ground, okay? Theoretically impossible, but it gives a very peculiar kind of wave pattern, but that's it. And pushes a lot of energy straight up. And the real ground is what we're using. There are two kinds, high accuracy and mini neck. Use mini neck when you have to ground something into the ground, okay? Neck 2 is not the best engine to use if you're doing studies that are highly reliant on grounds, okay? So we've now got a high accuracy ground, and that generates a ground description. There are two factors that you need to know about the ground. The first is the conductivity of it, and that's in Siemens or millimoles. It's 2 millimoles. And the dielectric constant of it, and that can vary all over the place. There is a handout I gave you that describes various grounds. The ground that we have in these models are for the Port Charlotte area down in Florida, okay? And they are what would be described as a poor ground, okay? And an average ground has a conductivity of 0.005 and a dielectric constant of 13. In Bruce's area, when we did that study, based on the information Bruce gave me, his area is 0.002 with a dielectric constant of 8, okay? So this is something you got to figure out. But if it's not exactly right, it doesn't matter exactly because it doesn't change a lot with those assumptions. It changes some though. And I'll show you that later. Okay. Let's open the 110 degree. And we'll go straight to wires. And you can see based on the handout I gave you for the 110 degree angle, it's model 2, that the dimensions have changed. The direction I got was to keep the wire at least 6 feet above the ground, okay? And I'm using the same length wire in all of these models, 32.5 roughly. And so when you do the math, this is where the wires end up, okay? You have an 18.6 height plus the 6 to get it off the ground, and 26.6 plus or minus for the y-axis. And so we'll look at the SWR for that.
Does this have the capability to do real 3D plots, Bob?
Yeah, well, those wireframes are, I guess, what the closest it can do.
You do the colored soap bubbles?
I think there's a way to do that. I haven't learned how to make it pretty yet. So if we look at the impedance, now it's 5337 with a J that is almost 0. So we're basically at resonance at, Mike, 7.203. Mike? Oh, Michael. The SWR is 1.067 at resonance. And Mike, resonant frequency is 7.203.
7.203 for
Yes,
version B.
right. And we're at 53.37 impedance. Okay. And if we do the far field plot, that's a three-dimensional plot that you can move around if you want, Steve, like that to get an idea.
Yeah,
Remember, the wire is going down the y-axis. Okay. If we do an elevation slice, what we find is that the gain is now 3.21 dBi, and the maximum gain is at 90 degrees like before. And these are the 3 dB points. And again, you can walk through it. We can look at an azimuth if you want, and look at the various elevations. And again, you can see it go from a circle to an oval, back to a circle. And there's more circle and less oval at this angle. Okay, next we'll load the third model. Okay, I did 90 degrees because the math on 90 degrees is so nice. The wires, well, they're 23 and 23 and 23 and 23 plus 6 to get us 6 feet off the ground. So, and if we run the SWR, I think I could probably reduce the fineness of this. We find that, let's see, I got to move you guys. The resonant frequency has moved up quite a bit, and the impedance has moved down quite a bit. So
Well, this is the C numbers,
yeah, this is at 90 degrees.
right?
So it's
So that's the
model
next,
3. Yeah. So the resonant frequency is now 7 point, just a minute, let me make sure I've got it right. Ah, there it is. Okay, 7.266. And the impedance at resonance is 46.32, and the SWR is 1.08. Okay, so now we look at this antenna and say, I kind of like that antenna, but we really want it to be resonant at 7.150. So how do we do that? And unfortunately, I don't have a sheet, a handout sheet, although I have made one. I forgot to send it out. But suffice it to say that if you do a ratio analysis, so the length desired equals the actual length times the ratio of the actual frequency to the desired frequency. So you end up with the 32.5 times 7.266, which was the resonant frequency of that plot, divided by 7.150, and you get 33.1 feet, okay, is the length of the wire now. So the wire's gotten longer. And let's see, am I on the right one? I am not. Let me open and get the right model. So if we look at the wires now, well, something got goofed up, but we're not going to worry about it. 23.4 minus 23.4. It's supposed to be 23.0, I thought, plus 6 more. So let's see what this gives us for a resonant frequency.
Da, 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 dum, da,
Exactly.
da, da.
Okay, there
All
it is.
right. See, it just needed a little music.
Yeah, that's it.
So this is D, correct?
Yes. So there's resonance, and resonance is at 7.141. Okay. So we haven't hit 150, and I think it's because of a math error I made in loading that model, but that's okay. It's close enough for
Amateurs.
For
amateurs.
That's correct.
That wouldn't be a bad antenna.
And what
SWR,
happens?
too?
The SWR goes to 1.079. The impedance is 46.36. And if we want to look at the gain, the gain is 3.33 dBi. And again, it's at 90 degrees.
One of the things I noticed in the plot, can you go back to the curve that shows?
Yes, I can.
When I'm doing things with antennas, there's no such thing as something broadbanded enough to be at 1.1 to 1 across an entire band. So I try and get things under 2 to 1 or better across an entire band if possible. And it seems as though that met that criteria that I normally have when
Yes.
I'm looking at stuff.
So it's 2 to 1 from 7.0 to, and I got to move you guys again, 7.3.
Jerry,
Huh?
it's 7 to Jerry on mine.
So
Hold your left hand up, Jerry.
Say again?
Hold your left hand up. Yeah, okay, that's where it's 2 to 1, your left hand.
Oh, you've got it superimposed on the other picture.
yeah. Okay, so now it's time for a roll call. Oh, I didn't do height yet. You want to see what happens with height?
Sure.
Are you worn out yet?
Can you show Smith charts from this and generate S2P files?
Yes.
SNP files? Okay, just curious.
Yes, there is a way to do it. From what I understand, I am not there yet.
Okay.
That's next month's presentation, right?
My brain is pretty much fried now.
I think all of ours is. That's okay.
Well, Can you
Ross and
imagine
I are
learning
sleep
this
deprived.
and doing a 160 meter four square array with an elevated ground plane?
You are definitely a glutton for punishment.
Anyway, okay, height. We are on, let's just use this model, the 90-degree model that is resonant at 7.14 instead of 7.15. And if we take the wires and how high do we want to make it?
30 feet.
Okay. So we're going to raise it by 24 feet. Okay. Because it's already at 6. Then we're going to run the,
So is that the apex, the height of the apex of an inverted V? Is that what we're looking at?
the apex is at 53.4 now. feet.
And it was at what?
Subtract 24 from that number,
Okay,
around 30.
30 feet. Okay.
Okay.
So we take the whole antenna and just put it up.
Raise it straight up.
All right.
Exactly.
Don't change the angles, don't change the lengths, just change how high the apex is, and that drags up the either end.
Exactly.
Okay.
So-
Just got to have a picture in my mind.
Okay, there it is. A
Can
picture
everybody
in-
see the picture in my mind?
Yes.
Yeah.
SWR. Any guesses on what's going to happen?
I would think it should be flattening out a little bit.
The standing
wire
wave.
frame.
Yeah, what'll happen to the, oh yeah, the wireframe, right. And, okay, the resonant frequency goes way up when we raise it because there's less interaction with the ground.
Yep.
Okay. In
So
fact,
if you calculate it for an apex sitting at 30 feet on or 50 feet on a 56-foot high tower, so that's where the apex is, and then you add another 10 feet to your tower so you can put it up further, you're going to have to change the antenna to get the same pattern higher above the ground.
yeah, but that resonant shift becomes less the higher you go,
Okay.
because you get closer and closer to being between Earth and Mars.
That makes
Right.
sense.
This is a textbook question, isn't it?
Huh?
This is a textbook question, isn't it?
It could be.
I could have sworn I remember hearing
And-
something with that or reading something with that when I was studying for my exam. Is
Yeah, it
the higher
might.
you go, the SWR changes.
Right.
Mike,
So you'll also see that the SWR is really nice now. Okay, 1.0009 or 009. And the impedance is 50.43 ohms. Okay. Very close to ideal.
Coax. And
The
that
coax.
means less loss in your coax.
Exactly. Okay, so let's look at the radiation pattern. Oh, Kiessel wins the prize. So it's flattened out considerably, and the gain point has started, the highest gain point has started to move down. So now the antenna is getting better for DX. Everyone got that?
Yep.
And if we look at an azimuth slice, it's oval like you'd expect.
So in other words, instead of being a cloud burner, it's more, the angle comes down, and so it it goes further across the
skip.
pond, so to speak.
Yeah, it'll skip now.
Yeah,
Right, but it's now becoming somewhat directional.
right.
That's correct. It's looking less like a vertical and more like a horizontally polarized antenna.
Not nearly as directional as I thought it would be.
No, well, if you keep raising
guess-
it, it gets
I
more
guess that's
direction.
because it's a inverted V and not a dipole.
Right, it's
That's
not a
correct.
dipole. It'd be more directional if this thing were flat. but
Yeah,
it's still an inverted V.
if we want to change the angle from 90 to 180 degrees, we could see what that looked like. But I have a feeling everyone's pretty much
Fried.
fried.
Yes.
So why don't we call it success? Does anyone want to report out on what happened as we changed angle, height, etc.?
Well, the resonant frequency, I was given the first thing. The resonant frequency went up as we progressively made the changes that we made.
Yep. Cecil, what happened with the SWR?
Well, the adjusted, the first one was 1.098, and this last one was 1. I have it here, 1.08.
Yeah,
So it improved.
improved a little bit, but pretty much, you know, didn't change very much at the resonant frequency.
Right.
But the resonant frequency moved all around. How about the impedance, Jerry?
It didn't change a whole lot. At 117, it was 54.89. At 110, it was 53.37. It dropped some at 90 to 46.32. Then when you kicked it up 30 feet, that went back up a little bit to 50.43. So all of them were right around 50 ohms, but they did vary a little bit. They went down a little bit as you tightened the angle until you raised it.
Exactly. Okay, how about the gain?
Yeah,
Steve?
well, the first one I have is 110 degrees, 3.21 dBi. At 90 degrees, the next was 90 at the same height, I think, 3.33 at 90. And then the one you just did was the one 5.09 at, where did I write the angle? Maybe I didn't write the angle. I thought I did.
Well, it's right here still. Let's see. Let me go back to an elevation. And that looks like 45 degrees.
Yeah.
Okay.
This has been fairly complex, but what I got from it is that you can look at what you're trying to accomplish. I want to get as close as I can to 50 ohms. I want to get to as close as I can to the direction that I want to point it at. And I want to get as low an SWR as I can get. And there are tweaks that you can make to it to not mess up the other functions and to get to the point where it's the best antenna for a particular direction and forward gain versus rear gain and impedance match. Correct?
Right. That's correct.
That's pretty slick.
And basically by studying variability, you know, changes, you also get a feeling for which factors have a big effect and which factors not so much.
Right.
Okay. So you get a much better idea of what to watch out for when you're making the physical antenna because it will impact the characteristics more.
Yeah, and I noticed as we got it further above ground, the less losses and the better it seemed to work. Obviously, this is at 40 meters. At 20 meters, you don't have to be as high to have the same amount of interaction. And And that sort of goes along with what I've known all along, that you want to get your 40-meter antenna or your 80-meter antenna as high as you can get it, because it's such a long wavelength that the ground affects it a whole lot more than it does at 20 meters or 10 meters.
Exactly. And the lower you are to the ground, the more energy you're shooting straight up into the clouds. That's
Right.
the other takeaway.
Yep.
The first antenna, the 117 degrees, was it?
Yeah.
I had that exact antenna in my backyard for a few years in California, and it was 6 feet up on a fence at one end. It hung from the apex from a tower, and then the other side ran across the roof and tied into the bottom branch of a tree. So I mean, but Fresno, California, where I was at, is pretty much in the center of the state, and it's about 185 miles to the San Francisco Bay Area, and that kind of thing. Sacramento, California, and about the same to LA. And some of the strongest signals I ever heard in that whole time were in the Bay Area and LA on 40 meters, data thing. And so that the NDIS thing, the near vertical incident, that is very true. And I've observed those same kind of that particular area where it had its strength.
Yep. So if you want to do DX, you want to try to get the thing as horizontal as possible and high as possible.
And so based on what we've heard tonight, this has been an inverted V on 40 meters. If we made it a flat top, a straight dipole, would that increase the distance for DX?
What it would do is it would bring this right here.
Right.
It would flatten the bubble, and this would get lower and lower.
That's kind of what I thought. Okay.
And, for DX, you want 15 degrees, 20 degrees, something like that.
Yeah.
You want to be able to get over any nearby obstacles,
Right.
but you want to keep it as low as possible so you have the fewest number of skips.
Yep.
Also, the angle at which you hit the ionosphere changes how much bounces back.
Right. Because the
Lower angles reflect more.
Yeah, because the closer you get to vertical, more of it goes through it as opposed to bouncing off from it.
Yeah, into outer space.
Yep.
Yep.
Well, you're skipping the stone.
Right.
That makes
Instead
sense.
of dropping straight into the lake. Yeah.
I presume this program has the ability to insert reactive elements like inductors or capacitors or things
Yeah.
there. Not to
Yes.
necessarily explore that, but
Well, it's okay. You can do loads. Okay. And this is where it would be. And you can have R's and you can have
okay,
L's and C's.
okay,
Okay. And then you can tell it whether that's a series with the wire that it's in, or is it in parallel with the wire that it's in.
okay,
And parallel means from where it's connected to ground, essentially.
okay.
The antenna that I was describing, I had a pair of traps for 20 meters. And you've seen I think is an 8 fellow, a K8, someone in this general area that did some coaxial traps, coaxial cable wound on some forms. He's been in QST lots of times, and they're kind of intricate little RG58U windings and stuff, but they work for the purpose. So I had 20 and 40.
Mm-hmm. Yep.
Is there a
Yeah.
website with like a reference website where people upload things they've modeled?
there probably is, knowing the way the internet works. I've been too busy doing things that I already had models for to actively go out and look at them and look for them. And I got to tell you, if you get an antenna book from ARRL, the CD is just packed with models.
Oh, for this program?
Yeah.
Ah,
This is a wire-based. Will this model a Yagi with
Yes.
4 segments?
Is this the
Yeah.
antenna book that you're talking about?
That's it.
Yeah, came with a CD. It has got a lot of good stuff on it.
Yeah, there's about 300 models in that book.
Yeah. Okay, here's a Yagi I'm designing right now. Oops.
Oh. You're in the save screen, not open.
Yeah, careful.
Yeah, I know. I've done this before. Okay, and that was this one, right?
You want to open it or save it?
I'm just gonna, no, I don't want to replace it. Okay.
You want to put on,
So,
just
now I
cancel
wanna-
out of this.
What happens is it automatically goes to save.
Huh.
If you're trying to open.
Just change the name to
There we go.
No,
You got
I just dumped it. Okay.
right.
And if I go down to, here's a Yagi I'm trying to do. And if we look at the antenna, there it is. Let me move Z down and zoom in.
Oh,
Okay.
that's a heck of a Yagi. What
Yeah,
frequency?
it's for 587 megahertz. Okay.
What's up there that you?
Channel 33 on television. I'm trying to get a Canadian TV station which has some programming that I'm interested in.
That's right. You mentioned that when we talked.
Yeah. So there is the Yagi, and here's the SWR. Okay. This ain't quite right, but oh. All right. I don't know why it's off like that. I would have to look at my notes to figure that out.
Right.
Show the plot on it, Bob.
I'll show the plot on it. Okay, I have 1 degree step size. Let me change that so the wireframe is a little more visible. It did 3 degrees. Let me do 5. It's got to be odd. I forgot.
It's got to be 6.
Huh?
Yeah, or they had to divide evenly into something.
Okay, so open that. Okay, and there's a wireframe of the antenna. And if we look at the elevation slice and show a 2D plot, okay, you can see that the gain is at 10 degrees, it's 18.37 dBi, which would be about 16.1 dBi, DBD, excuse me, gain over a dipole.
That's where the gain starts increasing very slowly.
Yes, I'm kind of at the limit,
Yeah.
but you know,
Bob?
at that frequency, they're easy to make.
Yeah. Bob?
Yeah.
Are there good tutorials for this stuff? This, in my opinion, you met the goal of this presentation, which was why should you want to get involved with this? I can see how this would be very, very useful for anybody that is trying to either tweak an antenna they already have or to create one from scratch to do a particular task. So now you've got my interest. Obviously, I don't feel comfortable that now I know how to do all this, but is there a good tutorial or wiki or something about how to do all this stuff? Because I'm not going to remember this, even though we've got it on tape.
Those 4 LB CBIC
Yes.
articles, okay, are a very good tutorial for a beginner.
Okay.
Okay, if you go to CBIC's website, okay,
Yeah.
it has white papers on various antenna related, modeling related topics that deep dive specific subjects.
Okay.
You want to learn more on a specific area.
Yeah,
Okay.
before he died, he released a CD that I was able to buy before he became a silent key. And it had 800 models on it. And so you can take, you can look into his model library and work forward. Bob, you said the best way to start is with a model that's something like what you want to do. And so I've always opened up that compendium and looked for something that looked like, oh yeah, that's kind of what I want to do, and work forward from that.
Cool.
And, you know, I don't know how much background you have on designing antennas, but I have a feeling it's at least as much as I had. And this is how much I've learned since Christmas, okay, about this stuff. So if you put your mind to it, but honest to God, there are nights, there were days I worked on it 8-10 hours, and at the end of the day, you know,
You felt like a wet dish rag.
You got it.
Yeah.
Okay.
Yeah.
I felt lucky if I could find my way to the dinner table.
Now, one other resource, Mike, is the ARRL used to have a course that you could take for certification on antenna modeling.
Yeah.
It's called the ARRL Antenna Modeling Course. It was $40, came with a CD. But the book, I've got the book, and you can still get the book from the ARRL. And it is a beginner's tutorial. It takes you from nothing to being pretty facile with this stuff.
Well, nothing's where I'm at right now, so it sounds like a good book to me.
It's the ARRL Antenna Modeling Course. I got the book. I'm holding the book. You're welcome to borrow the book if you'd like to do that.
Well, you're holding up the book, but I don't have any picture of you.
I know, because I'm not being me.
Yes.
Where am I? Oh, wait, I'm not being me at all.
No.
Okay, here I am being me.
Okay.
This
All
is
right.
the book, and it's I don't know, it's a couple hundred pages long. Let's see, page. Well, it's numbered by chapter, so I don't know what the total number of pages is, but it's a big book.
So it's antenna modeling course.
ARRL Antenna Modeling Course.
And use EZNEC or 4NEC too, huh?
Well, this uses EZNEC. I happen to prefer 4NEC 2. And the nice thing about 4NEC 2 is it'll read EZNEC files as opposed to EZNEC, which won't read 4NEC 2 files. So you can use either product with this tutorial. But this is a nice reference, Mike.
Yeah, and I'm looking carefully, and it's not focused in, but it looks like it's $40.
It's $40, yeah.
Yeah, well, that's reasonable.
Oh, yeah. And it came.
We lost your audio.
You lost mine?
Now you're back. It came with a CD.
Okay, yeah. Yeah, it comes with a CD with all the models discussed in the book.
Super.
Yeah.
Well, I can see what I'm going to be doing for the next year and a half or so.
Yeah, call the ARRL, see if they'll still sell you the book. I bought it after the course closed.
Really? Okay.
Yeah.
Well, Mike, you're way ahead of where I was when I started already. Just having gone through what you went through tonight.
Well,
Because none of this made any sense to me at all when I first started.
well,
It's a really good overview.
Yes, yeah.
And no, this is great, Bob.
It really, like, I was sitting here thinking, good Lord. But as we got further into it, I saw how you make a change and you see what it does. And the light came on, and in the the beginning of the blurb that I sent out says, have you ever wanted to be able to do your own antenna design? Well, this is a way to get started. And it definitely was that. You hit the nail on the head. So thank you.
Oh, you're welcome.
Yeah, very nice.
Thanks, Bob. Nice presentation.
Oh, he is alive.
Hey, Bill.
I do exist.
Well, we saw your picture, but I good to
I'm
see you in
here.
person.
Thanks.
Well, that's great.
I was struck that the numbers we were writing down looks a lot like the stuff we've been playing with the
Nano VNA.
DNA. Yeah.
Yeah. Yep.
Well, look at how powerful the two of these things are together.
Oh yeah.
Yeah.
Because you come up with what it ought to be and you put it up there, and then you see what it really is with the Nano VNA, and then you've got some kind of an idea of, if it's off, why it might be off. And
Right.
no, that's, and with the Nano VNA, okay, so you see the nice curve, but you don't know, it's a hit and miss, trial and error to get it the way you want it. Whereas that combined with this software, you'll know exactly what to do. Oh, I've got to get that at least 3 feet higher to hit the nail where I want to hit it.
Yeah, Mike, you only really get there by trial and error also.
Well, yeah.
Okay.
Yeah.
Okay, but at least you're not cutting wire and trying to move it in space.
Right.
Okay, it's much faster and simpler.
You're at least going in the right direction, as opposed to not knowing for sure, do I make it a lower angle or a bigger angle? Do I make it longer or shorter? You got some kind of an idea of what what it will take to accomplish what you want to do.
Mhm.
So
When you're out back, Mike, working on your stepper IR
yeah.
on the ground, just remind yourself, I got to lift this up someday. And all that adjustment.
Well, that's why I have waited to do it until it's warmer weather, because what I want to do is fix it on the ground, and then I will take all of the fiberglass tubes off, so it's just the boom that I can attach. I could do that almost by myself, and then you can attach the fiberglass poles once the boom was attached to the tilt plate on the tower, and then you just flip the switch and it goes up and you're done. So there is a method to my madness.
There's some madness in your method. Either way.
That too, yes, definitely. But
So Bruce, do you have any comments?
Yeah, I'm glad you asked, Bob. My first comment is that I was a recipient of all that great work where Bob killed himself on the 164 square, and he did a wonderful job. It was extremely helpful. Did a lot of detail on it, and you might want to throw up the 3D of the final product, showing the Foursquare how it looks on 160. The other comment I had was that an analogy for this is if you take an inverted V and put it on a pulley on your tower and put your VNA on it to rescan, scan, rescan, rescan, somewhere at the base of the tower, you can see all this stuff happen in real time. Very dramatic.
yeah.
So you get a really good feel like, oh, okay, well, if I move the ends of the elements out a little bit, I'm going to raise the resonant frequency, but I'm lowering the impedance of the antenna at the same time.
Yeah.
And basically, you can, in a short period of time, now you can't do this with a Yagi, you can't do this with other antennas. It just happens in an inverted V is real easy to do it with because everything is available to you. You can pull it up and down, you can move it in and out. You could even change the length of the elements a little bit. But it's cool. And, the modeling is definitely the way to go. Particularly if you live in Michigan and you've got all those months of the year where you can't really get outside and do anything anyway. So you might as well.
You gotta listen to a guy down in Florida tell you how nice it is down there every time you talk to him.
Right,
Yeah.
right. 82 degrees today. But yeah, there it is. So those are, that's the Foursquare I am continuing to construct right now. And
that thing is 15 feet above the ground. You can see the blue dot represents the ground. And
so show the radiation pattern.
let's see. Okay.
Yeah, Bruce, why did you put it 15 feet above ground so you could mow under it?
Yeah, so I could drive a tractor under it.
Yeah, that's what I thought.
There it is.
How's the spraying go yesterday?
I can still smell it in the field. I have to take the dog all the way out to the end of the driveway to the road to let the dog go to the bathroom because I don't want him walking in that poison. So there it is. I mean, it has a good front to back, but the front is really broad. The 3 dB beam width is like 48 degrees or something, isn't it? It's like very wide.
It's at
45 degrees.
the elevation angle's 20 something.
Yeah.
Hang on.
How wide is
The bandwidth.
Oh,
Beam width.
No, not the bandwidth. I mean the angle, the main lobe, how wide it is. How
That's the
direct-
beam
the beam
width.
width.
That's
Beam
We
width.
44,
need the azimuth view. Hang
Yeah.
on.
44.1 degrees.
There you go.
Yeah, there you go.
It's
That is
like 90 some degrees.
right. That's why you don't need 8 positions. You can design that antenna for an 8-position switch and phase it so that you can turn it in 8 directions. But you can see if you flip that thing up so it would be straight up at the 0 dB indication there, you'd only gain a couple of dB, right?
Yeah.
So nobody, few people have done that, but I don't think it's a wise thing to do. But this should be a good antenna on 160. I've had it up before, but never optimized to this degree. So I'm looking forward to it.
Yeah.
Wow.
It's a lot of work. I remember when we were putting your Foursquare together.
Yeah. Yeah. Well, that basically it's the same thing.
Right.
On
Just bigger.
although that one's ground mounted. Another reason not to put them on the ground down here is the ground is so lossy.
Yeah.
I'm on a sand dune here, and you really the ground losses go up when you try to put it on the ground.
Yeah.
Yeah.
How tall are the verticals for that?
If you look, if I could just for a second, the average gain when you look around the entire antenna is 0.371, which is -4 dB. So a good portion, more than half of the energy is getting absorbed in the ground, even with the elevated.
What's the reduction off the back end? In other words, it's sort of like a cardioid technique. And for noise immunity, you could point the trough at the noise source.
Yep, the back.
Well, you only have 4 directions you can point it, so.
We see the radiation pattern again. Asthma.
Yeah.
And Jerry, I think you asked, The wires are 131 feet, but you're starting 15 feet off the ground. So it's, what is that, 146 feet?
Each tower is 146 feet
Well,
high.
they're not towers, they're wires.
What's
But
it?
huh?
Are they hanging from something then?
Yes, there is non-conductive synthetic cables strung between the tops of the 200-foot towers.
Oh,
And at the right place, there's a pulley, and which is, you know, over 150 feet in the air, and then you just makes it very easy to, well, reasonably easy to just pull them up and down.
Bob, can we see the azimuth, please?
Yeah, I'm working on that. I'm not on my. There it is. Can you see it now?
No, that's the elevation.
Oh, you want the azimuth? I'm sorry.
Azimuth, yeah, thanks.
There you go.
Oh, yeah, nice.
And the front to back is 25 dB.
And but that's at the maximum gain, at the angle of the maximum gain, right?
Correct.
So it's probably, well, no doubt it's worse than that for some higher angles. You see that big little tail in the back that's sticking up? So if you get noise coming up, yeah, see that little tail? You get noise coming in at a high angle from the back, you know, it's not going to help you that much with that. But it turns out you can play with that a little bit by optimizing the phasing, which
Right.
It's still,
is an optional
well, it's
thing.
18 degrees down. That's significant.
Yeah, it's definitely going to help.
Yeah, for sure.
But it's not, that's what they tell me is it's about equivalent of a single full-size beverage. You can do, if for receiving, if you want to receive better than this, you have to put in phased beverages, like two beverages in parallel or offset, or, you know, with different spacings. There's a way you can phase your beverages to help reduce that back load.
Bruce, what's your noise situation down there in 160? Is it horrendous or okay?
It's pretty good. I have some power line noise to the west of me here, but generally it's pretty good. In the evening when 160 is open, it's atmospheric noise that's the limiting factor, not the you know, the power line and electronic noises.
Yeah, interesting.
Yeah, but I can hear it when with directive antennas here, I can hear the noise changing as I move around in azimuth. So there is noise. One day, if I'm here long enough, I'm going to go after the power line aspects of it. There's probably a noisy arrestor somewhere around here or something like that.
Yeah.
But I just, you know, there's just too many fish in the pan right now to try to go after that. But I have worked, you know, on a really a daily, nightly basis. In fact, I could turn it on right now. Well, I don't. Oh, I took out a piece of coax, so I can't get to that antenna. But I can work Europe virtually anytime, and Russia, Asiatic Russians, and you know, the English guys. They're basically on 160 all the time. But the trouble is they are the upper echelon. They are the guys that have big antennas and run the legal limit. If you want to work the guys on 160 that have the little antennas and running 100 watts, you're not going to do it until you go to the Foursquare or you get beverages so you can hear them. On the full size, because right now I'm running it just as a full size vertical. So
Well, unless we got any other things, it's almost getting close to 8:30. I think we should wrap this up, but it was, in my opinion, fantastic, Bob. Good
Great
job.
job.
Really
Thanks,
fantastic.
Bob.
Okay.
Yeah, Bob.
Well, I guess the key to this is not to spend too much time preparing.
I didn't give you much time, I know.
You did about the right amount, I'd say.
Yeah, yeah. Think of what would happen if I'd called him a week ago instead of yesterday. No, it wasn't yesterday, it was the day before. Or was
Most
it-
of the time I spent, well, it was Saturday morning's breakfast.
Yes, yes, it was. It was yesterday. Duh. My bad.
Fantastic.
Well, the truth of the matter is I had started working on this because I've been in communication with Doug over the last 2 weeks on this project.
Right.
And I kind of wanted to get an idea of, was this going to work or not?
Yeah. So this was a good dress rehearsal.
Yes, thank you very much.
Well, thank you.
Thanks, Bob. This is great.